Welcome to the Physics Odyssey channel. So the 2022 Olympics have been going on for about the last couple of weeks, and I've been watching a fair amount of it. And there's a lot of physics in these sports, and the sports I find the most interesting include speed skating, curling, aerial skiing, and figure skating.
Serikina looking good. You'll see the front end here. Try and guide.
Round, so he said, I'm going to do it. I'm going to do the highest degree of difficulty, 2 rotation.
I've created several videos which go into the detailed physics as well as the relevant mathematics of these sports. So if you like detailed physics and mathematical models as it relates to phenomena around us, then I think you'll enjoy these videos. But first I want to pitch my book. It's called The Physics for Space Travel. And if you want to become an astronaut, it's absolutely essential reading. You'll learn the physics and relevant mathematics of space travel, enable you to plan a mission to another planet in our solar system, or the moon, or launch a satellite, as well as to carry out the mission using the Orbiter 2016 simulator. It also includes a significant section on designing, simulating, building, and launching the model rocket, and also provides you the relevant physics and mathematics related to rocket aerodynamics. And there's also a simulator for that as well.
Of the US.
Okay, this is what I find interesting. Why isn't she rotating over? So if she were to come to a stop here, right, her velocity went to 0 right here, I don't think anybody would doubt the assertion that she would just fall over. So what is it that is keeping her from falling over? So before I give you my opinion as to what is keeping her from rotating over, let me give you some important background information. At this point of the course, the skaters are moving in a circle of this radius r, okay? Something that is moving in a circle is experiencing a force called centrifugal force. The magnitude of this force is the mass of, in this example, the skater, times her velocity squared, divided by the radius of the circle. And again, the radius of this curve is approximately capital R here. Now, centrifugal, some call it centripetal force, is a fictional force. It's caused by something. Okay, in this case, it's caused by the static friction between the skater's ice skate and the ice. The expression for this force is something called the coefficient of static friction times the skater's weight. Okay. Now, setting the centrifugal force equal to the static friction, that which is causing the centrifugal, gives me this expression here. Now, I can solve this equation for velocity by dividing both sides by mass, m, multiplying both sides by r, and taking the square root of both sides. So the velocity needs to be less than or equal to this number. If it's not, the skates will slide from out from underneath the skater, which is disastrous if you're in a race. Okay, so let me now explain what is causing the skater to essentially levitate and not rotate over. Okay, so there are two forces at work here. One force is the frictional force between the skater's ice skate and the ice, and that is producing the centrifugal force. Okay, and then you also have the gravitational force. Okay, so both forces are contributing to torque of the skater about this rotation point. Okay, so let's put some mathematical equations to this problem. Gravity is going to cause the skater to torque in a clockwise direction. Okay, so again, without velocity, the skater would just rotate over here and fall down. Centrifugal force is causing a torque in this direction. Okay, so counterclockwise direction. So it's a counter torque. Now, the levitation, right here, is experienced at this angle theta. Now, so what I've done is I have set the torque due to centrifugal, this expression, equal to the torque due to gravity, this expression. Okay, so let me explain a little bit more what's in this equation. So the equation for torque is force, here's the force, times r, and r is the distance from the rotation axis, this point, to, in this case, the center of mass of the skater, approximately where the star is located. The other part of the torque equation is sine of the angle between the r vector, again, r is pointing to the center of mass of the skater, and the direction of the centrifugal force. And that angle turns out to be this theta 1, right? Angle from the extended r vector to the direction of the centrifugal force. So I set the torque due to the centrifugal force equal to the torque due to the gravitational force. And the force is mg, just the weight of the skater. R is the same R as I used for this side of the expression, which again is just the distance from the rotation axis to the center of mass of the skater, times the sine, in this case, theta 2, the angle between this extended r vector and the direction of the gravitational force. So this is a requirement for the skater not to fall over. Okay, these are two different angles though. It'd be nice to have this expression in terms of the same angle. So if you look here, this theta 2 plus 90 degrees, that's 90-degree angle right there, is equal to theta 1. Okay, so what I've done here is I've substituted theta 1 is equal to theta 2 plus 90 degrees. So this expression becomes this expression. There's a trig identity which says that the sine of an angle plus 90 degrees is equal to the cosine of that angle. Okay, so I've replaced this with cosine. Okay, and just brought this forward. But the angle we're really interested in is this angle right here, theta, the angle of the skater relative to the ice. If you look closely here, this is a right triangle, okay? So 180 degrees minus 90 degrees minus theta here is equal to theta 2. So that gives us this expression here. So the next thing I've done is I've replaced theta 2 here in both expressions with 90 minus theta. So this expression becomes this expression. Okay, so starting with this equation, I'm just going to perform a little bit more algebra to come up with this equation right here. So what I've done here is I've replaced cosine of 90 minus theta with sine of theta, because we know that cosine of 90 plus or minus an angle is equal to the sine of that angle. And I've replaced the sine of 90 minus theta with cosine of theta, because we know that the sine of 90 degrees plus or minus theta is equal to cosine of theta. Okay, so this expression becomes this expression. The next thing I've done to get from this equation to this equation was to divide both sides by m times r. So this equation becomes this equation. Okay, the way I get from this equation to this equation is I divide both sides by cosine of theta. I multiply both sides by r, and I divide both sides by v squared. So that leaves us with tangent of theta is equal to rg over v squared. Tangent of theta is simply sine of theta divided by the cosine of theta. It's the same thing. Okay, so what does this expression tell us? It's very interesting. The smaller theta is here, this angle, the smaller tan theta is. Okay, so the higher the velocity of the skater as the skater goes around this curve of radius r, right, the smaller this ratio will be, therefore the smaller tangent of this angle will be, therefore the smaller the angle. So the faster the skater is moving, the closer the skater will be to the ground, the more leaned over she will be. This also tells us that the smaller the radius of the curve, in other words, the tighter the curve, the smaller the angle. Okay. So in conclusion, for the skater to maintain stability, in other words, not tilt over, this relationship must be maintained. The faster the speed, the smaller this angle. The tighter the curve, the smaller this angle. if the skater takes this curve at an angle such that this expression on the left-hand side is not equal to the expression on the right-hand side, stability will be violated and the skater will fall over.